Okay. The next question there is how many principal energy levels are occupied by electrons in astatine? Principal energy level means N. So that's the number in the front of each one of these. The highest number is 6. That means that levels 1 through 6 are occupied. So the highest energy level is going to be that one. And our total will be 6. Oh, by the way, I just want to make it very clear. If you write this on the test for your answer, I will take off many, many, many points because you can imagine reading 15 of these is going to give me a migraine. You need to differentiate between exponent and not exponent. Okay? Don't do this. This is terrible and horrible and torturous. So don't. This formatting is important because it helps because I can add up all of the superscripts and all the electrons that are in here too. And that would tell me if I've done my configuration correctly, at least partially, because I know if I've got the total number of electrons that I should have. Okay, so the notation here is important. You need to use brackets. The letters are all lowercase because an uppercase S looks an awful lot like a 5 for some of you. Not for my writing, but for different people it looks much more similar, so that's why they're lowercase. And so these are the rules. Follow them. Okay, so that answers number 3A and 3B. For 3C, I like to picture this as a diagram. So let me show you one. All right, so this is our electron diagram, right? We sort of looked at some of these in class. This one's complete. The one that we worked on before wasn't. It also organizes it by your L value, which is nice. All the S orbitals line up here, all the P line up, all the D line up, whatever. The ones in the book, the order of these, especially the D and the F and the S orbitals, tend to shift energy a little bit depending on what other electrons are doing. So these are not absolutely arranged this way, but it's a good starting point. Each principal energy level has a different number of sub-levels. So in the textbook, I think they use the phrase sub-shells instead of sub-levels, but it means the same thing. All right, basically sub-shell / sub-level is everything in the same principal quantum number. So here's one sub-shell for principal quantum energy 1. Here's 2 different subshells in the second one. The third one also has a 3D. So you can see I'm color coding here. The figures I gave you guys in your notes are actually already color coded, but the principal energy level is the same for the ones in the same color. So yellow is all the third energy level. There's 3 different orbital shapes. Each one of these is a sublevel. So this is a sublevel. Oops, I meant that to be in yellow, sorry. So this is one sublevel, this is a second one, and this is a third one. Okay, so we've got one sublevel here, 2 here, 3 here, on like that. Okay, so if our configuration ended at, let me see, what do we write? 6p5. So I can't really fit it into this figure on the iPad, but there's 5 electrons in the 6p orbital for our structure. The 4 has 4 subshells. The 5, in our case, we don't go above 6p. There is a 5f, of course, but we don't need it here. So I'm running out of color. The 5 energy level has 3 in it, and the 6 energy level in this case is going to have just 2 that are filled. Okay, I didn't draw all the arrows in here because it would be very, very busy if I did, but there's all the arrows below the 6p level. Okay, so like we basically just have to add this up. Okay, and so it's 1 in the 1 energy level, 2 in the 2, 3 in the 3, and then 4 in the 4, and there's like a pattern there, right? See? Cool. And then 3 and 2. So I think altogether we get about 15 sublevels. Okay, so that would be the answer to this question. Okay, so sublevels are like these little boxes, you know, this collection of space where the electrons can go at a particular energy level. Okay, so each one of those represents a sublevel. All right. The next question is asking how many orbitals are in the fifth principal energy level. Okay, so to go back to our structure here, the fifth principal energy level is 5d10 is our last, the fifth one that we filled in. So 5d10 means that everything except the F block is full for this particular thing. So in purple here, we have the 5s, the 5p, the 5d. The total number of orbitals is the total number of little teeny lines that are there. You can count them if you want. There'd be 5 in the 5d, 3 in the 5p, and 1 in the 5s. Or you can use a formula from the chapter and from the notes. And so you can calculate the number of orbitals, which is the shape, right? Individual shapes, by using the formula. Or you can think of it visually like we have here. So here we have 5 in that one, 3 here, and 1 here. So your answer for the number of orbitals, which is letter 3D, would be 9 of them. All right, so number 4. This is the more shorthand electron configuration practice. This is kind of the crux of the chapter. The first one, letter A, this is 4A, is going to be, so let's go back to our periodic table here. Okay. So here, sulfur is a non-metal. It is right here. And so the nearest noble gas before it would get us to neon. Okay. Too far. So I put neon in brackets. And then we have to go forward from there. So neon, and then that brings us to the third principal energy level. We have to traverse through 2 boxes, so 3s2, third energy level. The shape is S because we're in the first 2 groups, and we cross through both of them, so 3s2. Then I jump all the way over here. There's no d electrons in the third energy level, so we jump right to 3p. 1, 2, 3, 4. So 3p4. And that's sulfur. It has a total of 6 outer electrons. So, cool. For the next one, we're doing chromium. Chromium has the elemental symbol Cr, so that means it's right here. The nearest one before it is going to be in the end of group 3, because chromium's in group 4, so that's going to be argon. So we'll put argon in brackets. Okay, so we got that. And then we would say energy level 4. Angular momentum number, shape is S, and I go through both of those to get to chromium. Whoops, too far. So that knocks those ones out. Then we get to the D block, and I remember the D block, the transition metals, drops down by 1 energy level. So if it's period 4, which we are in period 4, that means this is the third energy level. And we have gone through 1, 2, 3, 4. So I'm going to write 3d4. Now, that's a good answer to begin with, but it's not the whole picture, because an interesting fact about pretty much all of the elements that are in group 6, which are these ones, and also the elements in group 11. It turns out that it's more stable to promote an electron and make the orbital half full. So like if we draw the picture of what this looks like, let me just import another photo for us. So here's our energy diagram. If we draw this picture of really, actually, let's zoom in. We're going to zoom in on the outer ones, 4s2, 3d4. Okay, So, sorry for the clutter, but we have 4s2, 3d4, all right? And so if I want to draw these electrons in, 4s2 means I have 2 electrons in my 4s energy level. They must point in opposite directions, otherwise I am violating the Pauli exclusion principle. For 3d4, we would go 1, 2, 3, 4. That means I have one empty box. And I want to spread them out as much as I can, and they all have to be pointing in the same direction, according to Hund's rule. I could also choose to point them all downward, like, it doesn't matter really which one you choose. Either way, we have 4 electrons, 4 different boxes, all pointing the same way. Okay, so here's the thing though. You'll notice the 4s and the 3d energy level are really, really, really close together. There is not a big gap, unlike between like the 1s and the 2s levels. There's a huge gap between that. Since that is true, one of these electrons can very easily jump up into the 3d orbital. And what happens when that occurs is it actually lowers the energy level of the 3d, because you have, we said that Hund's rule states that if the electrons all spin in the same direction, it's lower energy level. So if we take one of these electrons from the 4s and we put it into the 3d, it's actually going to mean the energy level here goes down. In fact, it even goes below the 4s energy level many times, depending on the element. So the true answer to this question, the subtle answer to this question, is the core is the same, that doesn't change, but we have taken one electron out of the s orbital, so that leaves us with just one there, and we have put it into the d orbital, because that is a lower energy state. This happens for everything that's in group 6. So as soon as I see an element in group 6, I think to myself, okay, that's not actually going to be 3d4, it's going to promote, it's going to be 3d5. So the best answer for this question is the one that's in red. Okay. So, that, like I said, that also happens for 11, because if you draw the diagram for, say, 3d9, which is what you would have for group 11, right, 11 valence electrons, every box would be full except for one. So if I promote one electron from the 4s, then I would have a completely full D shell. So half full and full D shells are favored. They have lower energy because of electrons being paired and because of Hund's rule, essentially. Okay, so we got to watch out for that with those. All right, so number C is the same element, but now it's an ion. So when something becomes a 3+, that means its charge is positive because it lost electrons, right? So the charge of something, as we learned in chapter 2 or so, is equal to the number of protons minus the number of electrons. So in order to have a charge of 3, chromium has, let's see, 24 protons. Okay, in order for this statement to be true, the number of electrons has to be 21. That means I lost 3 electrons by becoming an ion. Okay, so if it loses 3 electrons, they're going to come from the highest energy level. Okay, so you can imagine that the highest energy level here is going to be the 4, because we just had a discussion about how the 3D drops down in energy. So the highest number here is what I'm going to lose first. So the first electron to get kicked out is, let's do this in black so you can see it, is the 4s electron. And then I have to kick out 2 also from the 3D level. So what we end up with, I'm just going to write the 4s but with 0 electrons in it. Okay. 3D loses 2 because I have a total of 3 electrons to lose. So 5 minus 2 is 3. So this ion is argon core, no electrons in the S shell, and only 3 in the D shell. Okay. So then, for D, and by the way, this is why chromium forms so many different ions, right? It could lose 1 electron, which would just be the 4s. It could lose 6, which would be all of them. So that's why transition metals are crazy.